it starts from minus 90 degrees and it goes to minus 270 degrees. And here the magnitude starts from infinity and then it goes to 0. Okay? So here, even when I think about the gain margin, phase margin, etc., I always try to draw this figure first, and then I try to think about what is happening. This is what is happening in frequency domain. If you draw this thing so if you draw the magnitude and phase in polar coordinates, you get a Nyquist plot. If you draw the magnitude and phase separately, then you get the Bode plot. Okay? So here, at each point corresponds to a frequency. Okay? And this part is where frequency goes to 0, and this part is where frequency goes to infinity. Okay? And at the intermediate values, at each point you have a different frequency. And if you try to draw the magnitude and phase in polar coordinates, as in this case, you get some part of the Nyquist plot. And instead, if you draw these lengths in dB scale into a magnitude plot and these angles as phases into the phase plot, then you get the Bode plot. Okay. So in today's lecture, we are going to investigate what is going on in these Bode plots. So we are again considering the closed loop system given in the following topology. So we have G here, and we have H here, and we are given the Bode plot of GH. GH is the open loop transfer function. So we are given the open loop transfer function, its Bode plot. And based on that, we are saying something related to the closed loop. Okay? By looking at the Bode plot or the open loop system, we would like to say something, and we would like to design controllers for the closed loop system. Okay? So the task is the same as everything that we have done so far. In root locus we did the same, in Nyquist we did the same, in Bode plots we will do the same. So what type of factors can be in this GH? In this GH we can have some gains, K. We are assuming positive gains in this part. We really do not want to deal with the additional phase coming from negative gain values. So almost always we are considering positive gains in this part of the course. Integral and derivative terms, these are the S's or 1 over S's in our open loop transfer functions. We might have first order factors given in this form, or we might have second order terms like this. Probably the most important parts are gain, derivative and integral factors, and first order factors. These type of terms are encountered much less frequently in this part. So when I look at a single gain, which is gain K, in that case it would have the magnitude in dB scale, which is 20 log K, and the angle in degrees, it is 0 degree, because we are considering positive gains here. When we look at the first order factors with integral or derivative terms, we get this type of magnitudes. So here, if I consider an integral term 1 over s, then in frequency domain it is 1 over j omega. When I look at its magnitude, then I look at the magnitude of this thing. Its magnitude is going to be 1 over omega. And when I look at the dB scale magnitude, it is 20 log, this magnitude, 1 over omega, is minus 20 log omega. Okay? In a Bode plot, we are trying to draw the magnitude in dB scale. So this is y. That is what I'm plotting. I'm trying to plot it with respect to the x, okay, which is the logarithm of the frequency. Okay? In this part of the course, this logarithm is always base 10 logarithm. Okay? So this is log 10 actually. So we see that in this case, this is a line equation. In this case, y is equal to minus 20x. And what is the slope of this line? Is minus 20. So when you look at the magnitude here, you would see a line, okay? And the slope of this line would always be minus 20 dB per decade or minus 6 dB per octave. A decade would mean 10 times in this context. Okay, it means 10 times. So what happens when the frequency increases 10 times? If I increase this frequency 10 times, the magnitude decreases 10 times. When I take the logarithm of that, 20 logarithm of that thing, what does it mean for the frequency to increase 10 times? If I substitute here 10 omega, what happens to this 20x? If I substitute here 10, what happens? I would subtract minus 20 from here. Okay, so that actually means that the slope in this case is going to decrease by 20 dB if I increase the frequency 10 times. Okay, if I increase the frequency 10 times, the dB magnitude decreases by 20. Okay, or sometimes it is called minus 6 dB per octave. Octave in this context, it means 2 times. Okay, so when the frequency increases 2 times, then the magnitude decreases by 6 dB. Okay, that is what minus 6 dB per octave slope would mean. Okay, when you increase the frequency by 2, so if you substitute 2 omega here, what would you subtract from here? You would subtract minus 20 log 2 here. Log 2 is approximately 0.3, which gives you minus 6 dB. Okay, so here this decrease is from 1 to 2, you have 6 dB decrease. From 2 to 4, you have again 6 dB decrease. Okay, so from 4 to 8, you have again 6 dB decrease. So for the derivative factor, you have the same thing, but in this case, the slope would become positive. And here I have to maybe talk about the phase. If you consider an integral term, if you look at the phase of 1 over j omega, you would see that the phase is always at minus 90 degrees. So the phase plot for this thing is again horizontal, and it is at minus 90 degrees. So when we come to the first order factors, we are always in this course going to be considering the asymptotic plots. Okay? So here, if you have a term like this, 1 over s plus, let us say 2. The first thing that we are going to do in this case, when we try to draw the Bode plot of this thing, is that we will put this thing into Bode form first. Okay? When I put this thing into Bode form, I will take 2 parentheses here. This is 1 over, in 2 parentheses, 1 plus s over 2. This transfer function is now called in Bode form, because when s goes to 0, this term would bring me only 1. It won't contribute anything. And then I substitute j omega, 1 plus j omega divided by 2. Okay? So in this case, the frequency at which we have the magnitudes of the real and the imaginary parts are equal for this first order term is called the corner frequency, or you can actually say that it is corner frequency, and it is in this case 2 radians per second. In general, these type of terms would be written like this: 1 over 1 plus j omega t. And in this case, what is the corner frequency? 1 over t. So in this case, this becomes in seconds, and when you take 1 over this thing, you get the corner frequency. So here, you have to be really careful here. If omega is much smaller than the corner frequency, we're going to assume that this thing is almost exactly equal to 1. Okay? And if omega is much larger than 1 over t, we're going to assume that this thing is approximately 1 over j omega t. Okay? So in both cases, we're going to be neglecting one of the terms, and when we draw only these things, in such a case, we would actually say that is an asymptotic plot of the Bode plot. And in this course, we're only going to be interested in the asymptotic plots. Okay? So here is what I'm going to do. For magnitude, if this is my frequency 1 over t, for magnitude smaller than, for frequency smaller than 1 over t, I will assume that we are at 0 dB, okay? And for frequencies much larger than 1 over t, or larger than 1 over t, I will assume that this is going to be a first order term given like this. This is going to be the Bode plot that we are going to be using here. So if you look at such a Bode plot, this is omega. What is the slope here? What is going to be the slope? It is again going to be minus 20 dB per decade, or minus 6 dB per octave. So this is what you see in this case, and this is not an asymptotic Bode plot by the way. So this is an exact Bode plot, but asymptotic Bode plot would be fine for ourselves. So in this case, you see that for frequencies smaller than 1 over t, we get 0, and for frequencies larger than 1 over t, we get a line with slope minus 20 dB per decade. For the phases, we know that so this 1 over t here, I have 10 over t here, and I have 0.1 over t here. This type of term, what is the phase of this thing as omega goes to 0? It is 0, so I will assume that the phase is 0 here. And what is the phase as omega goes to infinity? As omega goes to infinity, this is going to be valid. What is the phase? Minus 90. So here, this Bode plot is going to be at minus 90 degrees. And what is going to be the phase when omega is equal to 1 over t? Minus, so in that case, I would have minus what? When this omega t is equal to 1, what do we have as the phase? Minus 45. So we have minus 45 degrees. So we see that this phase is actually going to do something like this. Okay. So that is a zero type. This was a pole-like term, and this was a zero-like term. It's just the opposite of the same thing. And when we look at the second order terms, again these differences. So here, what is different in this Bode plot? Sorry, I don't know how we flew this much, but for this first order factor, what is different in this Bode plot to this one, which is the asymptotic one? Where are the differences?
Just before 1 over t.
Yes, around this 1 over t, there will be differences. When the magnitude of omega is comparable to 1 over t, we're actually going to have some differences. For example, for the actual Bode plot, there will be a shift here, like 3 dB. Okay, so at this frequency, and this is just going to be the difference between the actual Bode plot and an asymptotic one. So when you consider second order factors, the differences would be actually increasing a little bit. So if you have such factors, this is again a quadratic factor in Bode form. If omega is very small in this case, again you have the magnitude 0, and if omega is very large, in that case you would forget about these terms if omega is very large. Okay, and then what do you have here? It is going to be just omega over omega n squared. In that case, again, we're going to have a j omega to the power like term, and what is going to be the slope in this case here? It is going to be in that case minus 40 dB per decade. Okay, so in this case, this is the case when the damping ratio is exactly equal to 1. And here, for small omegas, the angle is going to be 0 degrees. For large omegas, the angle is going to be minus 180 degrees. And we're going to actually be crossing the 90 degrees at the frequency omega n. So here, again, in this case, you are free to draw an asymptotic Bode plot, but you have to be aware that these asymptotic plots will be less and less accurate as the damping ratio gets smaller and smaller. Okay? If you decrease the damping ratio, you're going to see that these asymptotic plots will start to have a peak here. Okay, and this peak magnitude is really when might be proportional to 1 over psi, 1 over the damping ratio. Okay, but these peaks, as long as you are not given the exact Bode plot, you are free to ignore that type of peaks in your asymptotic plots. So now let us try to see how we can approach the problem of drawing a Bode plot. So here this is my open loop system now, and I would like to draw a Bode plot for this open loop system. Okay? The first thing that I have to do is actually to put it into Bode form. Okay? If I don't put it into Bode form, there might be some mistakes at the end, because each of the terms will start contributing a gain. So this term is not in Bode form anymore. So I have 20 s plus 2. To put this transfer function into Bode form, I will take two parentheses here. It is going to be 20 divided by 2. S will remain where it is, and I will write 1 plus s over 2 here. Okay? And I can cancel here this 20 and 2 here. It is 10, which is the gain. And I have s 1 plus s over 2. Now when s goes to 0, this term will not contribute anything. It's just going to be 1. But here, if I do the same thing, when s goes to 0, this term would contribute 1 over 2. Okay? So, which is what I don't want. I always want to collect all of the gain terms into a single term like this, so that these first order factors would always contribute 1 when I let s go to 0. And when I substitute s equals to j omega here, if I substitute s equals to j omega, I get 10 divided by j omega, 1 plus j omega over 2. And now I can determine what the corner frequencies are. The corner frequency of the j omega term, where is it?
0. Minus infinity.
Yes. So in this case, if you consider this one as a corner frequency, in general, this doesn't have any corner frequency that is going to be visible in a Bode plot. Okay. So here you can actually think that this term has a corner frequency at minus infinity. Okay. So here this term has the corner frequency omega is equal to 2 radians per second. Okay. So when I try to draw my Bode plot, I see that here there are frequencies 0.1, 1, and 10 here. Then I can mark this corner frequency as 2 here. Okay? And this is 0.2, and this point here is 20. Okay? And then I can put my 0 dB line here, and here there will be magnitude GH in dB scale. So now let us first try to draw the magnitude. I'm trying to draw this thing. So the first thing where on this plot is 0? Frequency is 0 radians per second. Where is it? Here? What is logarithm of 0? Minus infinity. It is somewhere there. Okay? So it is never visible. Frequency 0 is never here. Okay? So here we have frequency 0.1. This is my only corner frequency in this system. Now what I'm going to think about is that to start the Bode plot at some point for a small frequency, I will go to the left, go to the left as much smaller to frequency values much smaller than this corner frequency. For example, I can choose this value at which I'm going to find my initial value for the magnitude plot. I can choose it as 0.1. So for example, if the corner frequency is 2 here, I'm going to go at least 1 over 10 times that frequency. But here I will choose, for the sake of simplicity, the frequency 0.1, okay, as my initial point of the Bode plot. If we are at the frequency 0.1, then this term can be approximated as 10 over j omega, and this term is going to turn into just the value 1. Okay? So for a small frequency, omega is equal to 0.1, we're going to have this term, the whole transfer function would turn into this. Okay? What is the magnitude of this thing at the frequency 0.1? It is 100. In dB scale, it is 40 dB. Okay? So here, we are going to start the Bode plot at frequency 0.1 at 40 dB. Okay? And then, until I hit this corner frequency, this whole transfer function is going to behave like this. Okay? What is the behavior of this thing for different frequencies? It is just going to be a line with slope minus 20 dB per decade. So this is going to continue until here, for example, and the slope here is minus 20 dB per decade, meaning that I will hit 20 dB magnitude at this point. Okay? But until the corner frequency, this is going to continue. Okay? So this 20 dB, minus 20 dB per decade line is going to continue until here. So here, what is going to be the magnitude? This is, at this point, I'm at 20 dB magnitude. Okay? This frequency is twice the frequency here. So what is going to be the magnitude in dB scale? Yes?
20 minus 6, 14.
Yes, 20 minus 6, it's going to be approximately 14 dB. Okay? And then what is going to happen for frequencies larger than 2? For frequencies larger than 2, this 1 is going to be now negligible. Okay? So I will have 10 over j omega times j omega divided by 2. This is going to be my transfer function that I need to draw. And I know that such a thing would behave like another line. Okay? And in this case, that another line would be having the slope what? Minus 40 dB per decade. So here from 2 to 20, we are going to get minus 40 dB per decade line, and that actually means that around the frequency 20, we are going to be at where?
Minus 26.
Ne kadar proportional çizdim görüyor musunuz? Yok, iğrenç oldu proportionality ama kusura bakmayın. So this line here, minus 40 dB per decade line. Okay? So here, this was the magnitude plot, and I can now look at the phase plot. Again, I can have 0.1, 1, and 10 here, and I have the frequency 2 here. So here I have my phase is going to start from which degrees. So if omega is very small, this one would bring me 0 phase. Okay? What is the phase of 10 over j omega? Yes? Minus 90 degrees. If omega is very large, what is going to be the phase value of this thing? It is going to be, if omega is very large, this thing is negligible. I will have 1 over j omega square. Each j omega will bring me minus 90, meaning that the phase, if the frequency is very large, is going to be at minus 180 degrees. Okay? So the phase plot is going to end here, and it's going to start here. And at the corner frequency, where should we cross?
Minus 135.
Yes, it is going to be minus 135, because here at the corner frequency, this is still going to bring me minus 90, and this at the corner frequency omega is equal to 2. This is going to bring me minus 45. Okay, that means that we're going to hit the phase minus 135. We're going to hit at frequency 2 we're going to hit minus 135, and then I can just fill in the rest. More or less intuition. Okay, so now suppose that the earlier system, so this is the Bode plot of the transfer function that we have drawn. This is not asymptotic. This is the exact Bode plot, and based on this, we can look at the following closed loop system. In this case, GH is I have 20 s plus 2, and I have 10 over S, 1 plus S over 2. Okay? This was the system that we are considering. Now I can think that this GH is a part of the closed loop system. Okay? It is G here, and I have H here. And I can try to look at the phase crossover, gain crossover frequencies, and phase margin and gain margin of such a system. Okay? Now that is what we are going to do. When we have such a problem, we are going to have the Bode plot of the open loop system. We are already given the Bode plot, and based on that Bode plot, we can actually try to find these quantities. So before I can continue here, what about the polar plot in this case? What does the polar plot look like in this case for this type of system? For this type of system, what is going to be the magnitude as frequency goes to 0?
Infinity.
It is going to be infinite. What is going to be the angle as frequency goes to 0? Minus 90. So we are going to start from here, okay? And then, as omega goes to 0, magnitude is going to go to 0. From which angle we are going to go to 0 in the polar plot? The angle as omega goes to infinity is minus 180. So the polar plot of this thing would be looking like this. Okay? It is never going to be crossing the negative real axis like this. And if I complete this into a Nyquist plot, it is just going to be looking like this. Okay? So now let us try to look at these gain crossover frequencies and the other quantities. Gain crossover frequency is the frequency at which the gain crosses where? Gain crossover frequency gain'in diğeri kestiği yer. Phase crossover frequency fazın istediğimiz bir yer. X 180'i kestiği yer. Gain'in 0 dB'yi kestiği yer. So gain crossover frequency for this case is omega G. It is the place where it's the frequency at which gain crosses 0 dB line. It is here. Okay? So in this case, what is the gain crossover frequency? I have here 1, 2, 3, 4 radians per second. Okay, from the Bode plot I can read it. And then I can look at the phase margin. Phase margin is the phase of the open loop system at the gain crossover frequency plus 180 degrees. Okay? So here, if I look at 2, 3, 4 here, it is this value. So I'm going to add 180 to that. Okay? So I'm looking for this distance. Okay? Approximately how much is this distance? This overall distance is 45. Okay? So this is approximately
30.
It is something like 30, between 25 and 30. Let me say 20 to approximately 25 degrees. Okay? So this is my phase margin. And it is, in this case, positive or negative? It is positive. So that's good for our closed loop system. This means that the closed loop system is actually stable. So now let us look at the phase crossover frequency. Phase crossover frequency is where phase crosses minus 180 degrees. Where does the phase cross minus 180 degrees?
Should we say infinity or 20?
Yes, what should we say? That's the question.
100.
If you are, what is this number? Here at this point, it is 100 radians per second. If you are saying 100 radians per second, it's finished. So it's quite wrong. Okay, why is that? It is just looking like this is crossing minus 180, but it is never crossing minus 100, or it is crossing minus 180 where? At infinity frequency. Okay, so here we see that this magnitude plot would cross the negative real axis only at frequency infinity. Okay, that is why when you see something like this, that doesn't mean that we are crossing minus 180 at this frequency. Okay? That intersection is at plus infinity. Okay, So here I have omega p is infinite. And what is the magnitude there? I need to calculate the magnitude there. It is minus infinity. If I multiply it with minus 1, again, it becomes plus infinity. Okay? So here gain margin is plus infinity in this case. So what does it mean? I can increase the gain as much as I want. It really doesn't matter. The closed loop system would always remain stable. I have infinite gain margin, meaning that I can increase the open loop gain in this system as much as I like, and I will never get an unstable system. If I look at the root locus for this system, what does it look like? So I have here, when I look at the root locus here, it is going to be looking like this. This point is minus 2, and I will have the asymptotes even like this. I can increase k as much as I like. It really doesn't matter. There are never closed loop poles in the right half plane. Okay? That actually means that such a system would have infinite gain margin. It is also visible from the Nyquist plot. With which gain, if I scale this Nyquist plot, I will start encircling the point minus 1. It can be infinite. We will never encircle the point minus 1. That is why such a system would have infinite gain margin.
Hocam,
yes.
If you are given the approximate Bode plot of this system, like angle starts from minus 90 and ends at minus 180 at 20 frequency. What can we say about phase curve frequencies?
It is again going to be the same, of course. So even though you are plotting something like this, you have to be aware that frequency is never going to be minus 180. Okay? So even if you are drawing something like this, you have to be aware of the fact that this is not the exact one. So now suppose that into this system, I have the same closed loop system here, but the only change that I make here, I put here a gain, which is the gain 10. Okay? I add here a gain 10. Okay? In this case, I get a new closed loop system, and in that case, the performance measures of the system might have actually changed. Okay? This is the Bode plot of the original system, just GH here. From this Bode plot, can we read the closed loop properties, phase margin, gain margin of this system with this gain 10 here? Okay? Can we obtain those? So here, what is going to change in my Bode plot when I add a gain 10 here into the open loop?
You will shift magnitude plot by 20.
Yes. So what about the phase plot? Is it going to change? Phase is going to remain the same, but the magnitude plot should be shifted by 20 dB up. Okay? So I need to shift this, and I need to look at, in order to be able to find the gain crossover frequency, I need to look at where the shifted curve crosses the 0 dB line. Okay? Or if I want to use this curve instead, I need to look at the crossings of which line? With this one. I need to look at the crossings of this line with minus 20. Okay? So I see that minus 20 dB line here crosses this. Right in the middle of 1 and, this is 10. What is this? Burada genellikle problemi oluyor. 11 diyen de olurdu. Bu sene olmadı. Çok teşekkür ederim. Burada 11-12 diye gidenler oluyor. Mahvoluyorum. Ya 11-12 diye giderseniz burada hiçbir şey olmaz. 11-12-19'a giderseniz burada 20'ye geldiğiniz yerde 100'e gelmeniz lazımdı. Olmuyor. 10-20-30-40 diye gideceğiz. Okay? So here it is right in the middle of 10 and 20. Okay, I need to find that frequency. It's really not important. You can say 15, but here it would be interesting to see that. If I have two frequencies, okay, if I have logarithm of omega 1 and if I have logarithm of omega 2, okay, if I take the average of these two, what is this the logarithm of? Logarithm of which frequency is this one? Yes, this is the geometric mean. So if I look at the frequency here, this is going to be omega 1 times omega 2 square root. Okay? So in a logarithmic plot, if you would like to find the frequency corresponding to the middle point, it's not going to be the arithmetic mean, but it's going to be the geometric mean in that case. Okay, so here I can say that this is square root of 220 times 10. It is really not that critical. Even if you say 15 there, I wouldn't mind in an exam. Okay? So I would have here this value. What happens to the phase margin? In this case, what is this distance in this case? What do you think it is?
Something smaller than 25.
Yes, it's going to be smaller than 25. So let me say that it is approximately 10 degrees, or between 10 and 15 degrees. So while reading these plots, you have to make some approximations. Okay, it's never going to be exact. So you would have to use some approximate values. As long as they have some intuitive meaning, it is going to be fine. So in this case, the closed loop system is still stable because phase margin is actually positive. And I can look at the phase crossover frequency and the gain margin here, and both of them would still be infinite here. So now let us look at another system. So for this system, I would like to first read phase crossover frequency. It is where phase is going to intersect this minus 180. Where do we intersect minus 180 degrees? What is the frequency there? It is 2 radians per second. Okay, and then I will look at the gain margin. And in this case, I will look at the frequency 2. I have 20 dB magnitude for this system. So here, gain margin is the negative of the magnitude at the phase crossover frequency. What can you say about the gain margin for this example? Again, this is the open loop transfer function. We are looking at the gain margin of the closed loop system. Okay? What is the gain margin in this case? Yes? Minus 20 dB. What can you say based on this gain margin? It is an unstable closed loop system. With this open loop system, I have an unstable closed loop system. What can I do for achieving stability?
Multiplying with a k smaller than 0.1.
Yes. For example, if I make the gain smaller, and then I can try to obtain a positive gain margin. Okay. So for my frequency, phase crossover frequency will never change with a gain. Okay. But I know that if I make this magnitude smaller than 0 dB, then I know that in that case the gain margin is going to start becoming positive. Okay? In that case, meaning that if I shrink this magnitude by 20 dB, meaning more than 20 dB, meaning that I need to use a gain smaller than 0.1, in that case I will start getting a stable closed loop system. And now I can determine what the gain crossover frequency is. Gain crossover frequency is where gain crosses 0 dB line. Okay? So I'm going to be looking at this frequency here. It is 2, 3, 4, it's something between 4 and 5. So I'm going to write square root 20 here. And the phase margin is going to be, I'm going to be looking at the phase there, okay? So I will be looking at the phase here, and then I will try to read that number. It is approximately minus 220. What can you say about the phase margin? You will just add 180 to that. It is approximately minus 40 degrees. Okay? And this actually confirms that, again, the closed loop system is unstable. So suppose that I am not allowed to use any gain in the system to make the closed loop system stable. Suppose that I cannot use any gain. How can I make such a system stable? In that case, I need to add some phase here. Around the gain crossover frequency, I need to add some phase here. Okay? That is going to be one of our controllers that we see how to design. Okay? And it's going to be called a phase lead compensator. Okay? We will be able to add some additional phase to the system around the gain crossover frequency by something called phase lead compensator. Okay? And that is actually going to be able to make the closed loop system stable without adding much gain to the system. So when we look at the Bode plots, then stability and performance is usually going to be determined by the middle region. Okay? When you concentrate on a Bode plot, the middle region where you have these crossover frequencies will determine the stability and the performance. The low frequency regions, these low frequency regions will determine the steady state performance. Okay? So here, this part is going to determine the transient performance. Middle region will determine the transient performance. And low frequency region will determine the steady state performance. And in general, when you concentrate on the high frequency region of a Bode plot, that is going to usually determine the noise sensitivity of the system. If you have high gains of a system at high frequencies, then that means that such a system would be quite bad under noise. Noise usually enters at high frequencies into our systems. So if you would like to have, for example, a unit step or a sinusoid here, noise becomes at high frequency, added on top of this thing. Okay? So when you look at the high frequency regions of a Bode plot, you would have the slopes or how low those values are will determine how much this type of noise is going to be filtered in your system. Okay? So here, by looking at a Bode plot, by looking at a magnitude plot, can you determine the type of a system? The type of, for example, what was the type of such a system? If my open loop transfer function is given like this, if I would like to concentrate on the steady state error, what is going to be the type of such a system?
One.
It is just 1 in this case, because of this 1 over s. By just looking at the magnitude of the Bode plots, can you determine the type of a closed loop system? So yes, you can actually, if you concentrate on the low frequencies here, if in this example we saw that if omega is very small, these terms would always disappear. Okay? This type of terms would always disappear for small frequencies. That means that if we skip all of the corner frequencies, if we go to the leftmost part of a Bode plot, we will be able to see the number of integrators in the open loop system. Okay? And the number of integrators is going to be given to us by the slope of the Bode plot for low frequencies. Okay? If I don't have any integrator, what is going to be the slope? It is just going to be equal to 0. So your Bode plot is going to be looking like this. Okay? If we have a single integrator in the open loop system, then the slope at low frequencies would be minus 20 dB per decade, and you would actually see this thing here. If you increase the frequency 10 times, you will see a 20 dB decrease here. And you can actually look at if there are 2 integrators, the slope at low frequencies would be minus 40 dB per decade. So by just looking at a magnitude plot, you will be able to find the type of a system, and you would be able to determine the steady state error for the closed loop system. Okay? Actually, if you have also the phase plot, it is going to be even easier. If you have the phase plot, what is going to be how can you determine a type 0 system? What should happen to the phase if you have a type 0 system? Yes, exactly. So the phase is going to be 0 for a type 0 system. Okay? Phase for low frequencies. For a type 1 system at low frequencies, what is going to be the phase? Minus 90 degrees. For type 2 system, minus 180 degrees, etc. Okay, so this is using the magnitude plot, but for using the phase plot, you can actually try to do the same. From the Bode plot, you can actually determine these parameters, these static position error constants for the system. Okay, so by looking at the magnitude plots, we will be able to determine these, but they're going to remain for Wednesday. That's all for today. Thank you very much.
Hani feyizlerle type'a karar verebiliyoruz ya. Peki type 4'ten sonra 360 derece olduğu için repetition olacak. Bu noktada